Hey, what's up, Chem Peeps? It's Mr. Boylan. In this vid, we're going to identify a solution as being a buffer solution and explain how a buffer works to resist changes in pH. Basically, we're going to work our brain and get buffer. Okay, so breaking it down as always, really two things we need to do here. One, define a buffer and describe the important components of a buffer. So first of all, what the heck is a buffer? What's it made up of? The number dos. Explain the buffer mechanism in terms of the reactions that would occur on the addition of strong acid or strong base. All right, let's just get this party started. First thing, what the heck is a buffer? We need to define it. Well, a buffer is going to resist pH changes by neutralizing any added acid or added base. Again, it's just a solution that will resist changes in pH. All right, well, now we know what a buffer is. What is a buffer made up of? What does there need to be in order for us to be able to resist changes in pH? Well, a buffer will contain a weak acid and its conjugate base, usually the form of some soluble salt that contains the conjugate base ion, many times the sodium salt. So as you look at the example on your screen and in your notes, we've got a buffer between our weak acid, acetic acid, and its conjugate base, acetate ion. But the only way we can get that acetate ion in there is by adding it as part of a salt, in this case a sodium salt. But we're not really worried about the sodium ion, it's a spectator. Keep in mind, you can also construct a buffer from a weak base and its conjugate acid. But again, that conjugate is going to come from some soluble salt that contains the ion. Example in your screen and on your notes, we've got ammonia, a weak base, and its conjugate acid, ammonium, coming from the salt ammonium chloride. Again, the chloride would just be a spectator. Okay, buffer defined. Now let's talk about how buffers work. How do they resist changes in pH? So let's consider the general equation for an acidic buffer composed of a weak acid, Ha, and its conjugate base, A-. Now remember, we've got to have both of these things in solution in order to make a good buffer. And as we work through this, I want you to think about the equilibrium constant for this buffer system, this solution. And to understand how it resists changes in pH, we're just going to rearrange this equation to solve for hydronium ion concentration. Remember, hydronium ion concentration, we take the negative log of that to determine the pH of a solution. This equation is going to be super important. This rearrangement of your Ka expression is going to be super important for everything we do with buffers. All right, so how does it work? Well, when you add a strong base to a buffer system, there is a weak acid molecule there to neutralize it. In this case, we're talking about generalized Ha. So the formula, the equation to represent how it resists the change in pH is represented here in green. That weak acid molecule will react with the hydroxide ion to form more conjugate base and water, effectively neutralizing that added base. So as you think about your Ka expression for this buffer solution up here, rearranged for solving for the hydronium ion, sure, when you add the strong base, when you add that hydroxide ion, you are going to use up some of the weak acid and you will form some additional conjugate base, which will reduce the hydronium ion concentration. But without that weak acid there to neutralize that hydroxide, it would affect the pH much more. So here imagine our buffer solution all occurring here in water. If I were to add some hydroxide, there is some weak acid there that's available to neutralize it, sort of protecting this pH, this hydronium ion concentration. It will react with the hydroxide ion to form more conjugate base, but essentially protecting this pH of the solution. They can also resist changes in pH by the addition of a strong acid because there's a conjugate base in solution to neutralize them. So now we're going to focus on this, the conjugate base part of the buffer system. This reaction shows the general reaction for what happens in a buffer in order for a buffer to neutralize and resist changes to pH when a strong acid is added. The conjugate base reacts with the hydrogen ion to form additional weak acid. So again, think about your Ka expression for this buffer system, rearrange it to solve for hydronium ion concentration, and again, sure, we're going to form some additional HA because we're going to use up some of our conjugate base to neutralize that added hydronium. So sure, our hydronium ion will increase slightly, ever so slightly, but imagine if there were no conjugate base there to neutralize it. The pH would just blow up. Again, pictorially, now we're adding hydronium ion or H plus ion. We've got this conjugate base available to neutralize it. It sort of protects the pH of the solution that we have already. It protects the hydronium concentration. It creates additional weak acid. Boom. And again, the pH will change slightly, but not nearly as much if we didn't have the conjugate base there to neutralize the added strong acid. Okay, so that is essentially how buffers work and the reactions that you need to be comfortable with in order to better understand how buffers work. I really like this image that's on your screen and in your notes. Imagine your buffer starts here with equal parts weak acid and conjugate base. And depending on whether you're adding a strong acid or a strong base, there is something in your buffer system that is available to neutralize that thing that was added to essentially resist changes in pH. Now, it's important to note that buffers can only resist pH changes for so long, can only last for so long before it loses its buffering ability. We call this the buffering capacity, and it's just the amount of acid or base that you can add to a buffer without causing large changes in pH. So think about this animation once again. I've got initially equal concentrations of my weak acid and conjugate base. I'm going to add some hydroxide. Weak acid is going to neutralize it, form some more conjugate base. Boom. But now we're going to add some more hydroxide. Oh man. We're going to neutralize it with that weak acid that's available, form some more conjugate base. But watch out, now we don't have any more weak acid available. So any more hydroxide ion that we have is just really going to destroy the pH of this buffer system. There's nothing there anymore to neutralize it. It's going to attack whatever pH of your buffer system you had, make some water, and then any more hydroxide that you add, watch out, it's just going to destroy it. It's going to blow up the pH. All right, so two things then just to walk away with here before we end this vid. Recognize that the buffering capacity will increase with increasing concentration of the buffer components. The more weak acid and conjugate base that you have in your buffer solution, the more strong acid and strong base that it can neutralize. And two, recognize that your buffer capacity increases as your concentrations of the components become similar to each other, as your ratio becomes 1-to-1. Now that's important because a good buffer can neutralize the addition of both acid, strong acid, and strong base. And so you want to have equal amounts of each of your components so it can neutralize both acid and base, strong acid and strong base that's added. All right, finally, just check out this image. It's on your screen in your notes. I really like this. It really helps me to understand sort of what's going on with the buffer, or how we build the buffer, what a buffer is made of. Notice that you've got your weak acid component and take a look at the pH there. Notice we've got the conjugate base of that weak acid. Notice the pH here. And then when we combine them to make our buffer solution, it's going to have sort of an intermediate pH between the two. And we'll talk about calculating pHs and creating buffers with certain pHs in just a couple of vids. Have a fantastic day.